Hello and welcome. This is Chapter 2, Section 3, Finding Position from Velocity. So in the previous section, we introduced instantaneous velocity, and in turn, we were able to say that technically if you have a position versus time graph, then below it, you can find the velocity versus time graph just by looking at the slope of the position versus time graph. The slope of the position versus time graph is the value of the velocity versus time graph. And now we're going to turn that problem around. We're going to say if we know the position, or if we know the velocity versus time, what information can we say about the position? And there's two answers to that question. One is yes, and one is no. The first thing is that we can't conclude with where a specific particle is at its instant in time with the velocity versus time graph. So although you can't find an exact location from the velocity versus time graph, what you can do is find changes in position. And that's where an integral shows up. When you learned about integrals in calculus, what you looked at kind of the area. You looked at an area under a curve. What did that area represent? The area of that curve, which we would call the integral, that's the difference between two function values, at that initial and final location. And so let's look at that in the context of kinematics. So in this figure, we have, I think my slideshow got messed up. In this figure, we have a graph of velocity versus time. And so we can certainly find the integral by doing what we call a Riemann sum, which is just going through and putting these little rectangles. They don't have to be the same size, but it looks nice if they're the same size. They're all going to get squashed to zero anyway. And that area represents an incremental change in position. So you have to specify a specific starting position. Or in general, you have to specify a position at some time in order to know where the position is at everywhere else, because you're going to measure this area will be the change in position against the one that you're given. And so once we see a different formulation of the mathematics of uniform motion, instead of on the bottom here, instead of S sub F equals S sub I plus V sub S delta T, in general, that's only true for uniform motion. In general, the final position is always the initial position plus the area under the velocity versus time graph between the initial and final times. You have to be very careful about how much area you're taking so you get the displacement right. Certainly, this is helpful to go through an example. Again, the book has an example here. And what we see is a velocity versus time graph. Now we have V sub x. And again, the units of velocity being displacement over time, that's meters per second. Sometimes people like to write meters times seconds to the -1 power. That's nice. That's probably a little bit better. Either way, and then we of course have time in the seconds. So we have a velocity versus time graph that's increasing from 0 to 2 seconds. And so if it increases to 12 meters per second, or sorry, in 3 seconds, if it increases from 0 to 12, we're not looking for the slope right here. The slope of this graph has different physical meaning. We're looking for the area here. And of course, the area of this shape is just simple triangle, right? Areas of linear functions in general are always trapezoids. So they're always easy to do. Even easier if it's a triangle, right? Just half base times height. And so you just have 18, it looks like. The area under this curve is 18. But just like slopes, areas also have units. The units of this graph is, like any area, it's the product of the units of the vertical axis times the units of the horizontal axis. That's different from the slope. The slope of this line is the the units of the slope is the units of vertical divided by units of horizontal. Here the area is units of vertical times units of horizontal. And you can kind of see why that makes sense. You think about the area of a rectangle is just base times height. And so it's the same thing here. I mean, you just have meters per second times seconds. And so you get meters. Where does that show up on a position versus time graph? What you would say is that between 0 and 3 seconds, the position changed by plus 18 meters. So wherever you started out, the graph at the curve at 3 seconds will be 18 meters higher than the point at 0 seconds. And with this graph, we have a whole lot more information than that. We know the information for all time. And so you can kind of plot a smooth curve. Incidentally, it turns out that the shape of the position versus time graph would be, once again, a parabola, because the integral of a linear function, as you know from calculus, from the power rule for integration, the antiderivative rule, is squared. The integral of t is t squared over 2. Okay. And so they have a little bit of review about these integrals. Once again, this stuff is kind of assumed that you've gone through on your own, well, not necessarily on your own, but in a previous class. And we won't be doing too much heavy integration. The ones off the top of my head that I think could be important down the road for doing integrals would be, you have to make sure you can do integrals of exponential functions, which those are easy. You just have to get the factors right. You'll be integrating, you may be integrating powers. Of course, you could, in principle, integrate anything. And if, from a forward-thinking perspective, if you don't have a formula for the integral, you can always just use a computer to get as accurate an answer as you want. So that is the conclusion of the third section in chapter 2, and it's really kind of the end of the first part of chapter 2. In the next section, we're going to go through one of the most important topics in kinematics in all these in these first 4 chapters, because they'll show up in many places in this chapter and also in chapters 4 and also in many different future chapters. So thanks for your time. We'll see you back here for the next section. Take care.